We're talking today about various properties of liquids. Now these properties, we're going to talk more about this in the next little discussion, but these are all properties that are affected by intermolecular forces, which is something that we've talked about recently. There are a lot of properties listed here. We're going to go through each one of them one at a time, and then at the end we'll revisit the whole list. Surface tension is the resistance of the liquid surface to being penetrated by an object. So if you think about it, surface tension, it's sort of the skin on the surface of the water. It's the reason why when you do a belly flop in the pool it hurts, is because water has high surface tension. It has a high resistance to your body going through it. It's the reason why bugs can walk on water. So this is one of the water skimmer bugs. And it's because of water's high surface tension that this bug can essentially walk on water. It's also the reason why water forms these large beads. You can see the bead on the end of that leaf. And the upper right hand corner is a picture of various substances that have varying degrees of surface tension. On the left is mercury. It has a very high surface tension. Next is water, which has a moderately high surface tension. And on the far right is a liquid with very low surface tension. The bottom picture is mercury. The middle there is mercury in a little petri dish. And on the bottom right is a cartoon depiction from your book that is trying to just explain how surface tension works. And it's a nice little cartoon picture of molecules. If you put your molecule glasses on, you can see that the molecules, or in this case atoms of mercury that are in the middle of the sample, they are equally attracted by molecules on all sides. Because remember, these molecules feel a sense of attraction to each other, right? Even if it's just London dispersion forces, they're still attracted to each other. And of course, other intermolecular forces are even stronger. For example, water, hydrogen bonding. So the sample in the middle, those molecules are going to feel a lot of attraction on all sides, equal attraction on all sides. But the molecules at the surface are only attracted by molecules below it. There's nothing above it, and therefore they're sort of drawn inward toward the liquid, which is what gives it that rounded shape. Viscosity is similar. Viscosity is a measure of a fluid's resistance to flow. Viscous fluids flow very, very slowly, so high viscosity means it's a slow-flowing liquid. Low viscosity means it flows quickly. Viscous fluids are considered sort of, quote, thick. People describe them as being thick. In the bottom left picture, you see the samples on the right are the most viscous, and the samples on the left are the least viscous. I just liked the picture on the bottom right. That's why I put it on there. That looks like a pretty viscous fluid. That looks like glycerin or glycerol. Melting or freezing point and heat of fusion. These are related ideas. So melting point, freezing point is the temperature at which a liquid and solid will readily interconvert. Now, they're actually the same temperature. It just depends on whether or not you're talking about melting, the solid going to a liquid, or whether or not you're talking about freezing, which is the reverse process. So they're abbreviated T sub M or T sub F, depending on which one you're referring to. But they are actually the same temperature. So for example, water has a melting point and or freezing point of 0 degrees Celsius. Melting point, freezing point are like any temperature. They're measured in temperature units. That could be degrees Celsius if you're a scientist, or degrees Fahrenheit if you're anybody else in the US. Or it could be Kelvin if you're using an absolute temperature. Any of those work. Heat of fusion is similar. Heat of fusion is something you may have learned a little bit about last semester when you learned about thermochemistry. This is the heat associated with converting 1 mole of a solid into its liquid at its melting temperature. So fusion is another word for melting. And we'll do some calculations just to make sure everybody understands how to do that, but we'll do that. Let's first cover boiling point, which is similar in heat of vaporization. Boiling point is the temperature at which a liquid readily converts into the gas phase. Now, we don't really talk about a condensation point. Doesn't seem fair, but we only talk about boiling point. Abbreviated TB, and of course, again, measured in temperature units. The heat of vaporization is related. It is the heat associated with converting 1 mole of a liquid into its gas at the boiling point. Now, the process of boiling is something that I want to talk more about, and in order to do that, we really need to understand another property of liquids, which is vapor pressure. So let's talk about vapor pressure for a few minutes. Now this is a picture I got from that URL that's listed at the bottom of the screen. Vapor pressure is abbreviated PVAP. And in order to understand vapor pressure, we have a liquid in an enclosed container. This is an image of an Erlenmeyer flask with a stopper on it. You can imagine that this is any liquid that you're familiar with. Let's just say it's water. And what happens is, at a given temperature, some of the water molecules in the liquid phase will escape into the gas phase. And that's what those arrows are supposed to represent. So let's put some molecules in the gas phase. There we go. Now, this is going to continue to happen. This is the process of evaporation. So more molecules will go into the gas phase. Eventually, we'll get enough molecules up in the gas phase that they will start to collide with the walls, collide with each other, recollide with the surface of the liquid, and they'll start to lose kinetic energy, and they come back and condense back into the liquid phase. At a certain point, the rate of evaporation, escape into the gas phase, will equal the rate of condensation. And that will always, that what we call equilibrium will always be achieved. So now when you look at this picture, there's 3 arrows going up, there's 3 arrows going down, and that's supposed to represent equilibrium. So in this case, equilibrium is established when the rate of evaporation equals the rate of condensation. Equilibrium is a concept we're going to discuss much more in a couple of chapters, kind of in the middle of the semester. But for now, then you just need to understand that the forward and reverse rates are equal in this case. If we measure the pressure of that gas above its liquid, then that will be the vapor pressure. So the pressure of the vapor above the liquid at equilibrium is the vapor pressure of that substance. And that'll be a constant for a given liquid, a given substance, at a given temperature. Of course, if we change the temperature, that changes the vapor pressure. We're going to talk about that. But you can look these up in a table. You know, water has there's a table. If you Google vapor pressure of water, there will be different numbers listed for different temperatures. Our definition of vapor pressure up here. So vapor pressure, which is abbreviated P sub vape, is the pressure of the vapor above its liquid when at equilibrium. Now, let's talk about boiling and how vapor pressure is related to. So, let's talk about, first of all, if we change the temperature. If we increase the temperature, that has an effect on vapor pressure, and I want to explain why. If we increase the temperature, that increases the kinetic energy of the particles. That's something you learned about last semester when you learned about kinetic molecular theory of gases. And I have a picture here. This is from the textbook, and I'm going to go a little bit further into this picture. I want to talk about what these lines mean. This is our same picture, and I'm highlighting in blue sort of a lower temperature. Think about room temperature, and that's the number of molecules on Y that have a certain kinetic energy. Now at higher temperature, the graph sort of shifts over to the right, and that's the red graph. Now what I want to call your attention to is on the right hand side, past that dashed line, there is a blue shaded region. That's supposed to represent the number of molecules that would successfully escape into the vapor phase. This dashed line here is meant to represent the energy that's required for a liquid to escape into the vapor. And then at higher temperature, you can see that there's a much larger shaded region. And that's what's important here, is that we have many, many more molecules that can escape into the vapor. So we've seen the effect that increasing temperature has on the kinetic energy of the particles. And now if we think about it along with our Erlenmeyer flask representation with our molecule glasses on, then low temperature, say room temperature, then you'll have a certain number of molecules in the gas phase above the liquid. And if we increase the temperature, then since more molecules have sufficient kinetic energy to escape into the gas phase, we should therefore have more molecules in the gas phase above the liquid. And that should make sense. Now, if we measure the pressure of each of those gases, then the one at higher temperature should have higher pressure because there are more molecules in that sample, more gas molecules. Remember from last semester, PV equals nRT, and our Erlenmeyer flask on the right has higher N, right? More gas molecules. Therefore, it should have a higher pressure, and that should make sense based on what you learned last semester. So as the temperature goes up, the vapor pressure of any given liquid will increase. And it's not a linear increase. This is a figure from your book that shows 3 different liquids, ether, ethanol, and water. And you can see the effect that temperature has on each of those liquids. the effect has on each of those liquids' vapor pressure. Now let's talk about boiling. So we have a beaker at below boiling point, and what's going to happen here is it's just sitting on the counter, and some amount of evaporation is going to take place. And then we're going to talk about what happens as we increase the temperature and why that causes boiling. So we have our beaker, and we're going to put it on the counter at room temperature. Now, normally at room temperature below the boiling point of the liquid, there are going to be bubbles that kind of want to form, and they're going to push out with the pressure equal to the vapor pressure. Now, below the boiling point, what happens is the vapor pressure is too low and the atmospheric pressure is very large. And the atmospheric pressure will sort of crush those bubbles and not allow them to form. And that's because the atmospheric pressure is much, much larger than the vapor pressure. Right, so you see that there. So the bubbles want to form, but they can't. So as you increase the temperature, so let's give it a heat source now instead. And we're going to put that heat source underneath. We're going to erase the line, the beaker line, the counter. We're going to give it a heat source. Now what happens is when those bubbles want to form, the vapor pressure is larger than it was before. Because remember, as the temperature goes up, the vapor pressure goes up, and eventually it will equal the atmospheric pressure. And so now when the bubbles push out with the vapor pressure, then the atmospheric pressure will push back with the same pressure. And as long as they are the same, then those bubbles can form, or if the vapor pressure is greater, then those bubbles can form. And then because the air is less dense than the water, then they will rise to the surface. And that is the process that we understand as boiling. Okay, so we've looked at boiling, and now I've added in the right-hand picture, which shows what happens when it boils. So on the left, we're at room temperature. We increase the temperature, and that increases the vapor pressure. And eventually, the vapor pressure equals the atmospheric pressure. And those bubbles that were trying to form, they can now form because the vapor pressure equals the atmospheric pressure. The bubbles are not crushed, and they rise instead to the surface. So now let's give the formal definition of boiling point. So boiling point, or boiling temperature, is the temperature at which the vapor pressure equals the atmospheric pressure. Now that's the definition, and I also wanted to add in here, there's a demonstration on YouTube where a teacher takes a flask of water just below its boiling temperature, and she closes the flask, and then she cools it down. So the demo is called Boiling Water as It Cools. And it's supposed to make you go, whoa, that's so weird that I cooled it down and it started boiling, because normally you need to heat it up to make it boil. So the key here, and it's a really cool video, and it's only a couple minutes long. So take a look at that. But I wanted to explain how it works. Okay, so we have a flask, and this, I think I have here a round bottom flask. I think she probably uses a Florence flask, but that doesn't really matter. So we have a liquid enclosed in a flask, and there's going to be some gas particles in the flask as well. And so since it's enclosed, the atmospheric pressure now becomes the pressure of that gas inside the flask. Okay. And now as we change the temperature, what she's really changing the temperature of is that gas that's in the flask. So as you lower the temperature of that gas, then of course, because PV equals nRT, that lowers the pressure of the gas, which essentially lowers the atmospheric pressure, which means that as you know, since all you need to do is get to a temperature where the vapor pressure equals the atmospheric pressure, she's now lowered the atmospheric pressure. She doesn't have to increase the temperature as much to get the vapor pressure equal to the atmospheric pressure. And so instead of raising the vapor pressure, she's really just lowering the atmospheric pressure, and that's what causes the water to boil. So now this slide, this is the slide I showed you earlier, which just has all the little information and tidbits about boiling point. I added that last line, which is the definition of boiling point. TB is the temperature at which the vapor pressure equals the atmospheric pressure. And from that demonstration and from what we just said, I wanted to reiterate that this atmospheric pressure can be varied, okay? And it varies just depending on the weather outside even. If you want to boil water, it might boil at a different temperature today than it does tomorrow, depending on the atmospheric pressure. And if you travel up to higher altitude, it will boil at a different temperature because the atmospheric pressure is lower. So I wanted to also add the definition of normal boiling point. When we talk about boiling point of water and we say it's 100 degrees Celsius, that's the normal boiling point of water. And so that is a constant for a given substance. So the normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. That way, because atmospheric pressure varies, we can have a number that we can put in a table that's a constant. And that's going to conclude our slides